recording and sharing my screen. And when I share my screen, I came up with all of these really important announcements for the day. Today's September 30th. I can't believe it's the last day of September already. Wow, this year all of a sudden, as much as it seemed to drag, it's like flying by. The quiz needs to be done by the end of the day on the 2nd in my labs. The 2nd is Friday. Please submit neat numbered work in Blackboard. And some people last time kind of just sent me a piece of scrap paper, and it was kind of hard to figure out if there was anything there worth partial credit because I didn't know which question went with which. To try to keep it a little bit neater, please. Just a reminder, does everybody remember we are not having class on Friday because I have to go to a conference. Homework 7, which let me double check. Homework 7 is the one that is on combinations, is I believe to be done by the end of the day today. Homework 8, which is an introduction to probability, will be due by the 5th. And I got an email from a math organization that was talking about the mathematics of voting, and that made me think, oh boy, I haven't kind of said this often enough, but if you're not registered to vote, and you can register to vote, you still have time. Voter registration you can do up until October 9th. I believe you can do it online until October 9th, in person until October 9th. And if you're doing it by mail, your application needs to be postmarked by October 9th. If you're interested in doing it by mail, I know that on campus, the Student Life Office does have voter registration forms. I do believe that there is organizations coming in to help people to register to vote on campus. I have to apologize, I don't remember what days those are. But yeah, it's your civic duty to vote. In my mind, if you don't vote, you have no right to complain about anything that is going on in the with the government. Okay, I didn't mean to stop sharing the screen there. I meant to try to open the chat. Okay, it is pouring out at my house this morning as I was downstairs with my husband. He said that he turned his computer off because of the lightning. We haven't had anything like crazy happen here, but if I lose connectivity because of the lightning, I will try to come right back in. And if I lose connectivity at my house because of the lightning, you know, give me 5 minutes. If I'm not back in 5 minutes, we'll call it a day. Before we get started with that definition of probability, the last thing that we were looking at were problems with permutations and combinations, and some of the idea of how do you determine whether it's a permutation or a combination, which is based on whether order matters or not. That homework that involves that, I believe, is due by the end of the day today. Did anybody want to look at any questions in any of the My Math Lab homework?
The probability worksheet that you had emailed us, is that homework?
Oh, no. The probability worksheet that I emailed you is not homework. It's usually when I give notes in class, like when I give you guys notes, I don't have handouts for notes because I know that when I was a student, writing things out helped me remember it. And I've seen brain studies that more or less say that you know, writing out by hand, you're more likely to remember something than something that you just read off a worksheet or something even that you type. So, you know, that's why I'm old school with notes. It's not just because I'm old school, but because I've seen that that helps you remember. However, if I'm doing word problems or a whole bunch of examples, then I give a handout with those word problems. And so we will be working through those word problems. There's a chance we might start working on some of them by the end of class today. Otherwise, we will be working on them in class on Monday. And I know that some people like to have that handout in hand when we fill it in the notes. If we were in class, I would hand it out to you. And so I just sent it to everybody in email in case somebody wanted to have it to fill in when we got there, that you could print it out. Does that make sense?
Yeah.
Yeah, so it's not for homework, it's examples in class. And I did just put it in Blackboard, but then I got thinking, oh, you know what? It would probably be easy to email it to you as an attachment as well. I don't know which is easier for you to access if you want to try to print something out. So if you're, if it's easier for you to print from Blackboard, it's in there. If it's easier for you to print from an attachment in an email, it's in there. If you don't want to print it, you don't have to. I do have it attached, the word problems attached to the OneNote that I'm using for the notes. So if you want to just pay attention, you'll be able to download the filled in copy with the notes for the day. Any other questions on any of the homework problems?
From number 7, can you go over 3, like homework 7?
Sure. So homework, homework number 7. Sometimes it likes my finger as a mouse and sometimes it doesn't. Question number 3, did you say, hon?
Yeah.
Okay. There are 6 performers who will present, their comedy acts this weekend at a comedy club. One of the performers insists on being the last stand-up comic of the evening. If this performer's request is granted, how many different ways are there to schedule the appearances? With a question like this, there's a couple of different approaches that you can take. One would be like when we were looking at those first counting principle questions. We have 6 performers. There's one guy who wants to be last. If that person is last, then there are 5 left, and 4 left, and 3 left, and 2 left, and 1 left. And personally, sometimes I find it easier to picture some of these if I go through and look at the slots and say to myself, how many people are there available for each position? Does that approach make sense?
Yeah.
The other way that you can do it is you can say, okay, there's 6 performers. One's going to be last. And so that means that I'm really only looking at permutations of 5 of them. And that would take me to the 120. I do believe that in the Help Me Solve This, they use that factorial, their permutation notation. But again, sometimes when I'm looking at these and again, when it asks how many different ways, they're talking about how many different orders. Sometimes when I'm looking at things like that, I find it easier to fill in the slots. Okay.
I feel like there was more, I don't know, like more work to this problem. I don't know, when I was doing it.
No,
oh, okay.
With most of the permutation and combination problems, if it's a permutation, it's going to mostly be multiplying. When it's a combination, then you've got to multiply and divide. And I think most students feel more comfortable using a calculator to figure combinations than doing it by hand. And I don't have a problem with that. So, does anybody else want to look at any of the other homework problems?
Number 27.
Okie dokie. Oh, the last one. Usually the last one's the most challenging one. 6 men and 6 women line up at a checkout counter in a store. How many ways can they line up if the first person is the women and the people alternate woman, man, woman, man, woman, man? Okay, as I look at this, we have a couple of ways of looking at it. Again, this is one of those where I almost think it's easier to, again, take that fill in the blank perspective. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The first one's going to be a woman. There are 6 women to choose from. The next one's going to be a man. There are 6 men to choose from. The next one's going to be a woman. There's 5 left. Then there's 5 men left. Then there's 4 women. Then there's 4 men. Then there's 3 women. Then there's 3 men. Then there's 2 women. Then there's 2 men. Then there's 1 woman. Then there's 1 man. And if I look at that, if I pull those apart, that actually turns out to be 6 factorial ways of arranging the women times 6 factorial ways of arranging the men. If I remember correctly, 6 factorial is 720. And I have to apologize, I'm going to be a little bit of a slacker here. I can't multiply 720 by 720 in my head this morning. I probably should be able to. You know what? I probably can. So I got 2 zeros. 72 times 2 is 144.
518 400.
Thank you. 5-1. Final answer 518 400. Okay. Better?
Yes. 518 400.
Okay. You want me to type it in and see if we got it?
Yeah.
The problem is I lost my keyboard. There it is.
That's what I got too, so.
Oh. Yay! Fantastic! We did it! Woo! Does anybody else do a little happy dance when those words of encouragements pop up?
It's
I got to do something to stay active again. So tired of sitting in the seat in front of a computer. Does anybody else feel like they're spending too much time in front of a computer? Okay, never mind. Any others from the homework that anybody wants to look at? And so I guess moral of the story, when I'm putting people in line, for myself, personally, it's easier for me to picture that line. You know what I'm saying? So, all right, if those are okay, I'm going to back out of the homework and back into the notes. Did everybody get the important information at the beginning of the screen? I guess, you know what? Somehow I'm on the email list for one of my coworkers, and he emails like that type of stuff to everybody. Do you guys need that stuff in an email, or is just posting it in the notes at the beginning of class sufficient?
Email is good
Email is good?
for me.
Okay, I will try to remember to email you guys that stuff before class also. If that's all right, today we're going to start making use of what we've done with permutation and combination. And we're going to do that by looking at what most of this chapter is really about, which is probability. And we're going to see that a probability is the measure of the likelihood of something to occur. And before we actually look at how to find probability, we're going to define a couple of terms, a little bit of language that we'll be using. And the first thing I want to define is an experiment. And has anybody ever done an experiment? Nobody's answering me. Does anybody have like an experiment or something in science or something like that?
Yes.
When you do an experiment, isn't it you're trying to see what's going to happen. And you might have an idea, but you don't really know. So we're going to define an experiment as something where you don't know the result. You don't know what the results will be. In science, your experiments can be all sorts of fun and wonderful things. My daughter teaches chemistry, and she says she likes to start the semester doing something with the kids to make an explosion. We're not going to do anything quite that intricate. We're going to look more at things like, well, what are some events that we do that we don't know the outcome of? Beginning of every football game, don't they toss a coin? And why did they toss a coin? Because they're not sure what it's going to be. It could be one of a couple of different things. Some games you roll a die. Is everybody familiar with that word, die? If you have one, it's a die. If you have more than one, they're referred to as dice. I like to make the analogy, die is to dice, like mouse is to mice. Another thing that you do where you don't really know what the outcome's going to be is if you pick from a deck of cards. At which point, a deck of cards is frequently used as an example in probability. Is everybody familiar with what's in a deck of cards?
Yeah.
Yes.
Right. We'll look at that in a minute. And I want to show you another handout that I also usually give in this section. Is a picture of a deck of cards for people who have not played enough cards in their formative years, because there's really no prerequisite in life that you know what a deck of cards is. After an experiment, we talk about a sample space. And here we're going to find a tiny bit of overlap with that chapter that we just finished. This sample space is, you ready for it? The set of all the possible outcomes of an experiment. And so if I look at those experiments that we talked about previously, when I look at a coin, what's the sample space? What are the possible outcomes when I toss a coin?
Heads or tails?
Are you guys all right if I abbreviate heads or tails? When I roll a die, what are the possible outcomes?
1 through 6.
1 through 6. 1, 2, 3, 4, 5, 6. And if I look at a deck of cards,
52.
there's 52 cards in a deck. Those 52 cards can be broken down into different groups. When I look at cards, they can be broken down into diamonds, hearts, clubs, and I can draw this. Does that look like a spade? These two are considered red. These second two are considered black. And then in each suit, what numbers do you have?
1 through 10.
No 1 though. They start with 2.
Oh, there's 13 of each.
There's 13 of each. What else are there?
And Queen, Jack, Ace.
King, Queen, Jack, Ace. And ones
Excuse me.
that are considered the numbered cards. And the king, queen, and jack, if you look at them, all have a face on them. And so they're considered the face cards. Ace is not a number, and there's no face on an ace. As we're going through and doing problems, if there are problems that involve cards, and you're not real comfortable with cards, in Blackboard, in content, and handout, I have put that I would normally print out in color. Where is it? Here it is. And so if anybody needs this, if you're not that familiar with cards, there is a picture of a deck of cards. So actually there's a bunch of them. Usually I print out copies of this page and cut it out. But if you're not familiar, there's a picture of them. Then after we go through and define a sample space, the next thing that we're going to look at is, okay, I'm going to turn the page because it's not letting me scroll up. The next thing that we're going to look at is an event. And an event.
Can you go back to the other notes real quick?
Oh, now it did scroll. What did you need, sir? What part?
Just that part that's shown. I'm okay. Thank you.
An event is defined as a subset of the sample space. So it can be any subset of the sample space. If I'm tossing a coin, it could be getting a head. It could be getting a tail. If I'm rolling a die, it could be getting a 1. It could be getting a 6. Another subset might be an even number. Another subset might be an odd number, and so on. It's just any subset of your sample space. And so we're going to define the probability of an event. As the number of outcomes in the event over the number of outcomes in the sample space. So if E is the event and S is the sample space, I've told you that I'm lazy and I don't like to write. There's a symbolic notation for all of it. P of E is the notation for the probability of an event. And what we just said is that the probability of an event is equal to, check out what I'm writing. Does that notation look at all familiar? What's on the right-hand side of that equation? What does it mean when I put the little n in front of the parentheses? Remembering that E and S, the event and the sample space, are sets.
Numbers?
Number, right?
The cardinality, right?
Right.
We're saying that the probability of an event is the cardinality of the event with the cardinality of the sample. And so looking at that, start with some really simple examples that I'm guessing are things you might have seen before. But let's look at them and let's see if we can draw some conclusions from them. Let's say I toss a coin. What's the probability of getting a head?
50%.
50%. Can we write it as a fraction to start? There's one head out of two things in the sample space, which I guess if you wanted to, you could write that as 50%. I do believe most of the ones in my labs, I think they have you input fractions. Sometimes they have you input decimals, but is everybody all right going, just trying to use that definition? I'm going to start by writing them as a fraction. One head over two outcomes. What's the probability of a tail?
It's the same, right?
Yep. Tail out of the two outcomes. And if I look for are those my only possibilities?
Yeah.
If I look for the total of the probabilities of the single outcomes, in the sample space, I'd have 1/2 plus 1/2, which equals
2/4.
You're working too hard.
Oh.
One whole.
One.
Another half a pizza. When you put the two halves together, don't you have?
One whole.
Yeah. When you add fractions, just the real, because we will be doing some fraction addition here, they have to have the same denominator. So we're going to keep that denominator and we just add the numerators. That's, I think, enough of the coin. Let's look at the die. What's the probability of getting a 1 when I roll a die? There's 1 out of how many possible outcomes?
6.
What's the probability of getting a 2? 1 out of 6. What's the probability of getting a 3?
1 out of 6.
What's the probability of getting a 4? 1 out of 6. The probability of getting a 5, 1 out of 6. The probability of getting a 6, 1 out of 6. And if I look at the total of the probability of the single outcomes, if 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, which is going to equal help. The denominator 1 plus 1 plus 1 plus 1 plus 1 plus 1 is 6.
6.
1.
So we generalize and say that if I add the probabilities of all of the possible single outcomes, it will always be 1. Yes. So that's going to be the first rule that we look at. The sum of the probabilities of all single outcomes limit will always be 1. I want to play with my die a little bit. Everybody ready? On my die, what's the probability of rolling a 7? Well, there's 6 outcomes. How many of the outcomes are the number 7?
0.
None of them.
Wouldn't that probability be 0? What's the probability of rolling an 8?
0.
0. What's the probability of rolling a 10?
0.
0. What do all of those things have in common that have the probability of 0?
Just,
Can they happen?
no, they can't.
So can we generalize and say another rule? The probability of an event that's impossible is 0. Next examples. I'm still working with my die. I know it's getting old, sorry. What's the probability that I get a number less than 7? 6 outcomes. How many of those 6 outcomes are less?
6.
6. And 6 out of 6 is 1. What's the probability that I get a number greater than 0?
6.
6 out of 6, which is 1. And what do those two have in common? Do they have to occur?
Yes.
Yes. And so we're going to generalize there and say that the probability of an event that is certain to occur is 1. Okay, back to my die. I'm rolling it. What's the probability that I get an even number? How many evens are there?
3.
3 out. Which, yeah. Somebody, if you could mute until you're answering a question or asking a question, thank you. What's the probability of getting a number that's more than 2? Of those 6 numbers, how many of them are greater than 2?
4.
4. So that's 4 out of 6, which does everybody remember at some point in time reducing fractions? That would reduce to 2/3. When it comes to, if we were giving pencil and paper tests and quizzes, because we're looking at the definition of probability. On a pencil and paper and assignment, I would accept that fraction. However, in my labs, they always ask for it in simplest form.
Okay.
And so they're not going to give you credit if you don't reduce it. And so again, this is another one of those places where we're going to try to strong arm you into putting your work down in pencil and paper and submitting it when it comes to something like a test or quiz. Because on a test or a quiz, if you hit it wrong in my labs because you put in 4/6, I would go back and I would give you full credit. Or for that matter, if you hit it wrong because you reduced wrong and you had the right fraction, but you reduced it wrong, I will give you like 9/10 of the value for something like that. Because again, we're focusing on probability, not fractions here. Let's say I'm going to ask what's the probability that I get a number less than 6. Of 6 values, how many are less than 6?
5.
5. And do you notice that all of these answers outside of the 0 and the 1 are fractions? And so that gives me the next rule that I think you need to pay close attention to. Probability will always be between 0 and 1. The only possible whole number answers are 0 and 1. In my mind, this statement is kind of like saying in real life, everything falls somewhere in between being impossible and being certain. Either something must occur, impossible to occur, or somewhere in between. Probability is always between 0 and 1. And that's an important one to remember. If a question asks you about probability, your answer should always be a fraction or a decimal between 0 and 1. The only exceptions are you can have 0 if your event is impossible. You can have 1 if your event is certain to occur. So let's say I'm doing a long, drawn-out 3,000 part probability question. I worked for 20 minutes on this problem. My
Okay.
answer is that the probability of my event is, let's say, 39 over 38. What can you tell me?
It would be 1 whole plus 1.
This is over 1, so that's wrong. It's never over 1. And let's say I'm doing another one, and again, it took me a real long time to figure it out, and my final answer is negative 0.01. What can you tell me?
It's less than 0.
It's less than 0, so that would be wrong. It's never less than 0. So never put down an answer over 1 for a probability question. Never put down a negative answer, an answer less than 1. I'm sorry, less than 0 for a probability question. And remember that, because I can guarantee that there will be a test question and somebody's going to answer what's the probability with a number in the millions. Can probability ever equal a number in the millions? No.
No.
Smaller than 1. All right. I think that's enough of dice question. Let's look at a deck of cards. I'm going to pick one. What's the probability that it's a queen? We already set our sample.
4.
52 cards. There are 4 queens. The 4 queens are the Queen of Hearts, Diamonds, Clubs, and Spades. And that would reduce. Is everybody all right? They're both multiples of 4. And when I divide by 4, I get 113. What if I ask what's the probability that I get a red card?
After 52.
There's 52, and half of them are red. That would be a half. What's the probability that I ask to get a heart?
One-fourth.
Reduces to 1/4. Would be 13 out of 52. What's the probability that I get a face card?
Mm,
16.
Aces are not faces. Faces are the Queen and King. So there's 3 faces in each
12.
12
Like-
over
12 out of 52, or out of 30. What's the probability that I get the queen of hearts?
uh 1 over 52.
1 over 52. Next, I want to look at a bigger sample space. This time I want to say that I'm not going to roll 1 die, but rather 2 dice. So I'm rolling 2 dice. How many outcomes are possible? How big my sample space? How many-
12.
Where are you getting the 12 from?
So there's 6 numbers, and then so 6
Okay, so
plus 6 is 12.
Okay, but let's look at it. There's 6 numbers on the first die. There's 6 numbers on the second die. What does the counting principle tell me to do with those 2 numbers?
Oh, it's 36. Sorry.
Yeah, you got to multiply. And so
I-
36 possibilities. And so do you see how all of a sudden that what we were doing with counting kind of fits in with of this?
Mhm.
And so can we visualize those 36? My first die can be 1, 2, 3, 4, 5, 6. My second die can be 1, 2, 3, 4, 5, or 6. And I've seen in textbooks, very nicely written, all the possible pairs. I could have 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. Then we could have 2 and 1, 2 and 2, 2 and 3. And you get the idea in terms of writing them out. I want to say I'm not that patient a person. But a lot of times, instead of actually listing all the possible outcomes, I kind of just put those dots in there. I realized, for example, this dot would represent a 4 and a 5. Does everybody see what I'm doing here?
Yeah.
And when all is said and done, you see that there are 36 outcomes. And so if I roll 2 dice, there are 36 possibilities, because the possibilities are the pairs of outcomes. What's the probability that I get a sum of 1? What's the probability that my 2 dice add to 1?
0.
0. What's the probability that I get a total of 12? How many of those would add to 12?
Just 6 plus 6, so
6 plus 6.
only 1.
There's only 1 out of the 36. What's the probability that I get a total of 5? And with these, I sometimes find it easier if I go through and I draw my sample space out with the dots and think of circling those possibilities. So in order to add to 5, let's see, it could be a 4 and a 1,
The 2 and the 3.
a 2 and a 3, or a 1 and a 4. And so that would be 4 out of 36, which would reduce to 1/9. Now, sometimes that picture kind of help you count them. What if I ask, what's the probability that I get a total less than, let's say, 20?
That would also be 0, right? Because highest you can go is 12.
Right. And if I want a number smaller than 20. Arms
Oh,
raised is smaller
so
than 20.
just a whole, that would just be a whole 1 then.
It's 36 out of the 36 are 1. It's something that must. And I'm just looking, I forgot to do something, I apologize. What time do we have? Oh crap.
Hmm.
There's also an idea of empirical probability. And I'm looking at my watch. And my watch says we have 1 minute left. And so I'm going to make note that I stopped here.
Okay.
And we'll pick up here. When I look at empirical probability, I am going to be pulling some examples out of the textbook. So just realize that I'm going to be using the virtual textbook when we go over this empirical probability concept on Monday. All right? So, okay, that having been said, where did the time go? Is it me? Did that go fast today or no?
That went very fast.